From the light that's letting you see the screen to the sound hitting your ears, our world is just constantly humming with activity. And the messengers carrying all that energy and all that information, well, they're called waves. So let's dive in and really unpack what they're all about.
I want you to start with a picture we all know. Just imagine it. You toss a small stone into a totally calm lake or pond. What do you see? Yep, you see those perfect little circles, those ripples, just spreading outwards from where the stone hit.
Okay, so those ripples, that's a perfect example of a wave. And right here on the slide is the core definition that kind of changes everything. A wave is a disturbance that transfers energy, not stuff, from one place to another. But water molecules themselves aren't actually traveling to the edge of the pond. Only the energy from the stone splash is making that journey. It's a huge distinction.
And this idea of energy on the move is the absolute key to everything. Seriously, it's the one concept that ties together every single type of wave we're about to talk about.
So how in the world does this work? Well, imagine a little cork floating on that pond. As the ripple passes under it, the cork just bobs up and down, but it stays in pretty much the same spot, right? It doesn't ride the wave all the way to the shore. And this just perfectly shows our point. The particles of the medium, the water in this case, they just oscillate, they just vibrate in place while the wave of energy keeps on moving forward.
Now you might be thinking this is all just about water, but that's not it at all. Waves are fundamental to almost everything we do. You could say they're like the invisible architects of our daily lives. Just stop and think about it for a second. The sound of my voice is reaching you right now through sound waves. Your phone? It works by sending and receiving electromagnetic waves. Even the ground beneath our feet can transmit these incredibly powerful seismic waves during an earthquake. They are absolutely essential carriers of both energy and information.
So since there are so many different kinds of waves, physicists needed a way to organize them all. Think of this next part as a sort of field guide, something to help us identify waves out in the wild. And we're going to start with the biggest distinction of them all.
So the first big split is this. Does a wave need stuff to travel through? On one side, we've got mechanical waves. You can think of them as needing a helping hand. They have to have a medium, like air or water or a solid, to get anywhere. But on the other side are the cosmic travelers, electromagnetic waves. They don't need anything at all and can zip right through the empty vacuum of deep space.
So for example, sound waves need air molecules to vibrate. Water waves obviously need water, and if you shake a rope, the wave travels along the rope itself. All of these are classic, textbook examples of mechanical waves. And get this, here's the really mind-bending part about this other family of waves. They don't need any medium. None. This is the whole reason we can see light from stars that are hundreds of light years away. That light has traveled through the pure nothingness of space to reach our eyes. Radio waves, X-rays, they all belong to the same incredible family. Okay, so let's zoom back in on that mechanical wave family for a second. There's another way we can sort them, by the direction the particles are vibrating. In what's called a transverse wave, particles move up and down while the energy moves forward. They're perpendicular to each other, exactly like when you shake a rope. But in a longitudinal wave, the particles push and pull back and forth in the same direction the wave is traveling, kind of like a slinky compressing and stretching out.
Okay, so now that we've met the families, let's learn to speak their language. To really be able to describe a wave, we need to understand all its different parts. So any wave, it doesn't matter how different it might seem, can be described using just a few key properties. You can think of these as a wave's vital statistics. They tell us everything we need to know about its unique character. First up is amplitude. This is really just the wave's strength or its intensity. It's the maximum distance a particle moves away from its resting position. So a tiny little ripple has a really small amplitude. A tsunami, on the other hand, has a massive one. The key takeaway here is super simple. Bigger amplitude equals more energy. When we have wavelength, you'll often see it shown with the Greek letter lambda. This is just the length of one complete wave. And the easiest way to picture it, just measure the distance from the very peak of one wave, we call that its crest, to the crest of the very next one. Simple as that.
And rounding out our key properties is frequency. This tells us how often the wave cycles, or you could say the number of complete waves that pass by a certain point every single second. We measure it in something called hertz. So a low-frequency wave is made of these slow, lazy vibrations, while a high-frequency wave is just all about rapid, super energetic vibrations. So here's a fun question. What happens when two waves run into each other?
Do they, like, crash, bounce off? The answer is actually way more elegant.
It turns out they follow this rule called the principle of superposition. I know it sounds really complex, but the idea behind it is beautifully simple. When two waves occupy the same space at the same time, you just add them together. They pass right through each other, and for that one brief moment, their amplitudes combine. And this simple addition leads to two really fascinating outcomes. If the crests of two waves line up perfectly, they add together to make a much bigger, more powerful wave. That's called constructive interference. But what if the crest of one wave lines up with the trough or the low point of another? Well, they cancel each other out, which results in a smaller wave, or sometimes no wave at all. And that's called destructive interference. Pretty cool, right? So let's pull all of this together. When you step back and look at the big picture, from the tiniest ripple in a pond to the light from a distant galaxy, waves are pretty much the universe's main way of moving energy and information all over the place. So what are the big takeaways from all this? First and foremost, remember that waves move energy, not stuff. We also learned their speed depends on what they're traveling through, and that they are absolutely vital for all of our technology. We saw they come in two main families, mechanical and electromagnetic. And finally, we discovered that when waves meet, they don't crash, they interfere with each other. And this quote really says it all perfectly. Understanding waves helps us unlock everything, from building our communication systems and medical imaging devices to even designing musical instruments. They are truly fundamental to how we perceive and shape our reality. And that leaves us with one final thought. Beyond the sounds you're hearing and the light you're seeing, just think for a second about the Wi-Fi signals, the radio waves, and all the other invisible vibrations passing right through you at this very moment. What invisible waves are shaping your world right now?